Hi friends, now let's discuss about the resonance. In organic chemistry, there are a number of compounds for which we cannot explain all the properties drawing just one canonical structure. We need more than one canonical structures to explain all the properties of a compound. Let's take an example of the benzene. In benzene there are 3 double bonds and 3 single bonds between the carbon atoms, and therefore we can expect that a carbon-carbon double bond, this bond length should be shorter than the carbon-carbon single bond. So therefore we expect to have 2 types of bond lengths in the benzene, one shorter, one a little bit longer. And in an isolated single and a double bond, we know that the bond length between the 2 carbon atoms, between a carbon-carbon single bond, it is 154 picometers, while as a carbon-carbon double bond, which is a little bit shorter, it is 134 picometers. So in benzene we can expect to have 2 types of bond lengths, one a 134 picometers and the other one a 154 picometers. But experimental evidences tell us something different. Experimentally we find that all the bond lengths are same. In benzene, all the bond lengths are same. All the bond lengths are same. All the bond lengths are same. How much? Not equal to 134, not equal to 154. It's in between, about 139 picometers. Which means that in benzene, if all the bond lengths are 139, which is shorter than a single bond but greater than a double bond. That means in a benzene we don't have a localized double bond, we don't have a perfect double bond or a perfect single bond, right? These things we can, these properties of the benzene we can only explain by the help of a resonance. But what the resonance means, right? So let's see what the resonance means. Resonance is actually the delocalization of pi electrons, right? I'll repeat, it is the delocalization of pi electrons. If pi electrons get delocalized in a system, in an organic compound, that's a resonance. And for the resonance, it's important that the molecule should be conjugate. We should have a conjugate system. So that is the very important requirement for the resonance. Conjugate system means we should have alternate single and double bonds, right? We should have alternate single and double bonds, single and double bonds, right? Like in the benzene, we find that there are 3 double bonds, but the 3 double bonds are alternately present. We have a double bond here, single, double, single, double, single. So that means this is a conjugate system because we find double and the single bonds alternately present. So therefore these pi electrons can delocalize. That means in benzene resonance does occur because we have a conjugate system, right? So therefore the pi electrons can resonate, right? They can delocalize here. These electrons, these pi electrons, they shift here. These pi electrons shift here. These pi electrons shift here. And the first structure now changes to the second structure. This is the canonical structure 1, canonical structure 1, and this is the canonical structure 2. The second canonical structure changes back to the first one by further again delocalization. And the hybrid, the actual structure, is represented by the hybrid structure. So this is the hybrid structure, which is the actual structure. These canonical structures we call them as canonical structures, and these are the contributing structures of the hybrid structure. And if we can have a double arrow between the canonical structures, but these 3 parallel lines to represent a hybrid structure, right? So this is about the resonance. So resonance is delocalization of pi electrons, and for the resonance we should have a conjugate system. But that's not the only requirement for the resonance, right? There are 2 essential conditions for the resonance. Number 1, the conjugate system. The molecule must be conjugate, right? That means there should be alternate single and double bond. The second requirement is that we should have a planar molecule, right? Planarity is another requirement. We find that in benzene that all the carbon atoms are sp2 hybridized, and sp2 hybridized carbon is planar. If all the sp2 hybridized carbons are there, that means the molecule is planar, right? So this is the second requirement for the resonance. The one, we should have a conjugate system. The second, we should have the planar molecule. In resonance, we have all these requirements. In benzene, we have all these requirements. We have a conjugate system, we have a planar molecule as well. So therefore resonance can occur, delocalization of the pi electrons can occur, and because of the delocalization the molecule becomes stable. The hybrid structure, which is the actual structure of the benzene, that is very much stable. So higher the delocalization, more, that means more the resonance, more will be the stability, right? So let's take some other examples of the resonance, right? So this is another molecule which is called as a 1,3-butadiene, because we find 4 carbon atoms, 1, 2, 3, 4. This is a 1,3-butadiene, right? In this molecule we have a double and a single bond alternatively present. So this is a conjugate system. Resonance can occur here, right? So we can shift this pi electron here and this can shift here, right? And you get another canonical structure where you find a double bond between the center, between the carbon number 2 and the carbon number 3, and you got here a negative charge here, and you got a double positive charge over here. So that means the structure first, it changes back to the second, structure second, and structure number second changes back to the structure first. So the two canonical structures interconvert, and what we find here, the two canonical structures here, they have a little bit energy difference. They are not equivalent, right? These are the two resonating structures of the 1,3-butadiene. Okay, we can draw the hybrid structure for the 1,3-butadiene over here by dotted lines, right? Okay, which means that the pi bond, the pi electrons are under resonance, right? The pi electrons are under resonance here. The hybrid structure here is very much stable molecule, right? Out of the two canonical structures, the first and the second, right? The first one is more stable than the second. The first one is more stable canonical structure than the second. Why? Because in the first structure we find 2 bi-bonds. Here you find only 1 bi-bond. Higher the number of bonds, remember, higher the number of bonds in a canonical structure, more will be the stability. Among the canonical structure there is some energy difference, the stability difference. The one with the more number of bonds is more stable canonical structure. So here you find 2 double bonds, here you find only one pi bond, so that means the structure number 1 is little bit more stable than the structure number 2, right? So there is the energy difference. So these are the non-equivalent canonical structures. These are the non-equivalent canonical structures. In benzene they are equivalent canonical structures, right? So I'll write down here again the benzene molecule. We know that in a benzene there are 3 double bonds, right? So they interconvert the structure 1, it changes to the structure 2 by resonance. So delocalization of pi electrons, now pi bond is formed here, here and here. So the first structure and the second structure, they have the same number of bonds, 3 pi bonds here, 3 pi bonds here. So these are equivalent canonical structures, right? These are equivalent canonical structures, but these are non-equivalent canonical structures. And among the non-equivalent canonical structures, the one with the more number of bonds is more stable canonical structure, right? Among the two, this is the most stable, and this structure 1 will be contributing more towards the hybrid structure, right? So let's take another example. Not only the pi bonds, right? If they are in conjugate system, they can undergo resonance. If you have a lone pair of electron, right? If you have a lone pair of electron and then a single bond and then again a double bond, it can also undergo resonance. The lone pair of electron pairs with any atom, if it is at the allylic position, then it can also undergo the resonance. We have a double bond, a single bond and a lone pair. It can also undergo resonance here. So the resonance will be like this. It will shift in this direction, and the second canonical structure you will find a double bond between these, the nitrogen and the carbon, and a negative charge over here. The nitrogen gets a positive charge. So these are the two canonical structures, right? Again, the structure number 1 is more stable than the structure number 2. Why? It's not because that the number of bonds is different. You see here, we have a 1 pi bond, we have a 1 pi bond. So number of bonds are same, right? Number of bonds are same, but why A is more stable than B? Is because we have a charge separation in the second, right? Here we have a charge separation. The same molecule, a positive end and a negative end. Here in this molecule is all about neutral, right? There is no charge separation, right? If the number of bonds are same, then we can check which one is more stable from the charge separation. If there is charge separation, a positive and a negative end in the molecule, that is relatively less stable than the one which is neutral. So that means the structure number 1 is more stable than the structure number 2, right? The structure, canonical structure first, is more stable than the canonical structure second, right? So due to the resonance, what happens? Delocalization, right? So let's take another example of the resonance. The lone pair of electron of the nitrogen, it can also undergo resonance because we have a lone pair, a single bond, and then a double bond. It can also shift here, and the second structure that you will get will be like this. You will have a double bond between nitrogen and the carbon. You get a negative charge over this position, and you got a double bond over here. The nitrogen gets a positive charge, right? Another structure, you can see this double bond goes down, this lone pair goes down, it goes up here, and now at the para position a negative charge, a double bond is here, 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 and a positive charge on the nitrogen. Again you will find a further resonance. It goes down here, it goes here, and therefore you can have a negative charge on the ortho position, double bond at this position, and at this position, with the nitrogen having the negative charge. So these are the 4 canonical structures. First, this is the second canonical structure, this is the third canonical structure, and this is the fourth canonical structure. Out of the 4 canonical structures, the first one is more stable canonical structure, so therefore it will be contributing more towards the hybrid structure. While the second, third, and the fourth, these are almost the equivalent. These are almost the equivalent canonical structure. They don't have the energy difference, right? Next point here is, due to the resonance, we know the molecule becomes stable, right? The molecule becomes stable, and suppose we have a 1,3-butadiene. Here we have a 1,3-butadiene. The structure number 1, it shifts here and it goes here, right? Electron pair, now you find a double bond between the second and the third. You get a negative charge on this carbon, a positive charge on this carbon. So this is the canonical structure second, and it goes back here, and you get the first canonical structure. So these are the 2 canonical structures, and the first one is more stable than the second one. Relatively, the first one is more stable than second one, right? The hybrid structure is the most stable structure, right? So the hybrid structure is the most stable one. Due to the resonance, when pi electrons delocalize, what happens? The molecule becomes stable, right? So that means the hybrid will be having the least energy. The hybrid structure has the least energy. It's most stable, right? But what the resonance energy mean? Resonance energy actually represents the energy loss which occurs due to the delocalization of pi electrons. When pi electrons delocalize, the molecule releases energy, and that energy is called as the resonance energy. And the resonance energy is actually the energy difference between the hybrid structure and the most stable canonical structure. Out of the 2 canonical structures here, the first one is the most stable, right? The second one is not. It's having a little bit high energy than the first one, right? So in terms of energy, we can draw here a graph, energy graph for this one. So we can say, suppose this is the hybrid structure here, this is the hybrid energy of the hybrid structure, this is the energy of the first structure, and this is the energy of the second structure, because first one is more stable than the second. So the difference here, energy difference between the most stable canonical structure, which is in this case the first one, and the hybrid structure, that is the energy gap that you find here, that is actually the resonance energy, right? The energy has been released actually, right, when the molecule undergoes resonance, correct? So the resonance energy is the energy difference between the hybrid and the most stable canonical structure. The resonance energy of a compound, it is the measure of the the stability of the conjugate system, right, compared to the isolated system. If you have, suppose, a double bond, right, but the double bonds are not, suppose they are not conjugate, suppose you have a double bond here and here, but if you have a system where you find a conjugate system, this one is less stable than this one by the amount of resonance energy, right? Because in the first case here we do not find the resonance because this is not a conjugate system, so resonance cannot occur. In this case resonance can occur, right? So due to the resonance, this molecule is more stable than this one, and the difference in energy will be equal to the resonance energy, right? So higher the resonance, say the greater the resonance, greater is the stability of the molecule. Like in the benzene, we find the resonance energy is about 36 kilocalories per mole. So that means when resonance occurs in the benzene, the energy release is there, that's about 36 kilocalories. The resonance energy of a compound is calculated from the difference between the theoretical and the experimental value of the heats of hydrogenation. For example, the heat of hydrogenation of a cyclohexene, which contains one double bond, the heat of hydrogenation, when we add a hydrogen here, the heat of hydrogenation for the cyclohexene, to get a cyclohexane, is about 28.6 kilocalories per mole. So if this is the heat of hydrogenation of one double bond in a cyclohexane, so accordingly we can expect that the benzene should have the heat of hydrogenation 3 times this, because it has got three double bonds, so 3 hydrogen atoms should be. So you can expect, if this is the heat of hydrogenation of a one double bond, then therefore we can say for the benzene, the heat of hydrogenation to get a cyclohexane must be equal to 3 times the abodita, that is 3 times the 28.6 kilocalories, which will be equal to 85.8 kilocalories per mole. So this should be the heat of hydrogenation of the benzene. Theoretically, we can say the heat of hydrogenation of the benzene must be this much, 85.8. However, experimental evidences, right? Experimental evidences are different. Experimental value of the experimental value of the heat of hydrogenation for the benzene, is not this much. It's not this. Rather, it is a little bit lesser, about that is 49.8 kilocalories, right? Kilocalories per mole. We expect to be 85.8, but experimental value of heat of hydrogenation for the benzene is 49. So this is lesser, right? So there is some difference. The difference in the theoretical value and the experimental value. How much is the difference? The difference here we find between the experimental value and the theoretical value is that 85.8 minus 49.8, that is 36 kilocalories per mole. And this is the resonance energy of the benzene. So this is how actually we calculate the resonance energy. We calculate it from the heat of hydrogenation. If we have a double bond which actually does not undergo the resonance, which is a localized double bond, right? If you do the heat of hydrogenation, that is experimental evidences, that is 28.6. So therefore we can expect if one double bond has this much, then 3 separate double bonds should have this much, right? That is 85.8. Experimental value is for the benzene is 49.8, not this much. So the difference that we find between the theoretical value and the experimental value, that is the resonance energy, right? So that means That means benzene has energy about 36 kilocalories per mole lesser than what we were expecting. So that means the benzene is more stable, right? Benzene is more stable than what we expect, right? So the resonance energy of the benzene molecule is 36 kilocalories, right, by which the benzene molecule gets stabilized. If there's more resonance energy, more the difference here, more will be the stability. Let's take some other examples of the molecules which undergo resonance. Not only the double bonds, right? Suppose if we have a double bond, CH2 double bond CH single bond CH, we know that there is a resonance in this molecule. We have a conjugate system. Resonance is also possible if you have a double bond and then a single bond and then an atom with the positive charge. Here this positive charge on the carbon, it can also undergo delocalized. The resonance is also possible in this molecule as well. The this carbocation, the carbon with the positive charge, it is electron deficient, so electron pair will shift in this direction, and another resonating structure for this molecule will be CH2, single bond, CH double bond, CH2. Here this is only one CH, it's not a CH2. So the positive charge will be over here. These are the two resonating structures and they are equivalent because we have equal number of bonds and the charges on the carbon here and here also. So these are the equivalent resonating structures. Similarly, the resonance is possible if you have a double bond, then a single bond, and then a carbon with negative charge as well. You can also delocalize this negative charge. Right? We have a double bond, single, and a negative charge. Here was the double bond, single, and a positive charge. You can resonance, the carbocation can be delocalized, the positive charge can be delocalized, the negative charge can also be delocalized, but the electronic push will be in the opposite direction. Here the pi bonds, they move towards the carbocation, which is electron deficient. Here the carbon with negative charge, it is electron rich, so this electron pair will not shift towards this, rather it will shift in this direction, and here it goes down. So therefore the another canonical structure will be like this, CH2 negative here, then a single bond, CH double bond, CH2. Again, these two canonical structures are equivalent canonical structures, right? Because number of bonds is same, and we got here a negative charge on the carbon, negative charge on the carbon. So electronegativity difference is same, so the stability difference will be almost zero between the two canonical structures. So that means the double bonds, when they are present alternately, they get resonance, right? They are delocalized. Resonance occurs here. Positive charge, if it is in the conjugation, if it is at the allylic position with the double bond, that can also undergo the resonance as well as the negative charge, right? So if you have suppose another molecule where you find an atom, any atom A with the electron pair, with the lone pair, right? This lone pair also gets delocalized. In the same way we got here the negative charge, right? So this negative charge goes down here and this goes here, and what you get? You get another canonical structure, CH2 negative single bond CH double bond A, and here gets the positive charge. But now these two canonical structures are not equivalent. There is the energy difference. The first one is more stable than the second one because we have no charge separation here. Here you find the charge separation, the positive and the negative ends within the same molecule. So these are the non-equivalent canonical structures. These are equivalent canonical structures. These two as well equivalent, right? And the structures you get from here, again they will be non-equivalent, right? Because from this molecule it will look like this, right? If you have a double bond, it goes delocalized over here, you get a negative charge, single bond here, and then a double bond CH, then a CH2 So you get here the negative charge, you get here a positive charge. So again, this one is not this one is more stable than this one, because we have 2 pi bonds. Here we got the 1 pi bond, and the second point, there is no charge separation. Here you find the charge separation between the two. So therefore the first structure here, this one is more stable than this one. These are the non-equivalent canonical structures, but these two are equivalent, these two again equivalent, and these two non-equivalent canonical structures. So I hope you got the basic idea of the resonance. We have to study the resonance a little bit more when we study the different types of reaction intermediates. We'll discuss the resonance and the effect of the resonance in stabilizing the different molecules and the reaction intermediates. Thanks for watching the video.